Welcome back to Cosmic Sedation, where the stars whisper secrets and galaxies hum lullabies. Tonight, we drift into the topic Bok Globule B68, a quiet ballet of gravity. Subscribe if you're enjoying this cosmic journey as much as I am. Drop a comment letting us know where you are tonight and what time you usually fall asleep. It's always fascinating to hear from fellow space travelers. Now, let's begin our gentle descent into the night. In a region of space so cold it approaches absolute zero, Bok Globule B68 is not merely resting, it is alive with motion. At minus 263 degrees Celsius, each dust particle within this cosmic cloud dances to its own gravitational waltz, colliding and coalescing over eons. This dance is not random. It follows the subtle pull of gravity, guiding particles toward a common center as they lose energy and settle into a denser configuration. For comparison, if you were to enter B68, your body would freeze nearly instantly due to the extreme cold, yet the pressure would remain low enough that you might survive in a pressurized suit for some time. This peculiar environment has been collapsing under its own gravity for only about 500,000 years, a fleeting moment on cosmic scales, but long enough for these particles to have made countless collisions. The dust within B68 is not merely floating, it is actively shaping the future of star formation in our galaxy. Each particle collides with others at velocities averaging just 1 meter per second, slower than a gentle breeze on Earth. These low-speed impacts cause the cloud to contract, gradually increasing its density from roughly 10,000 molecules per cubic centimeter to potentially form stars. To put this into perspective, while B68 is incredibly sparse compared to our atmosphere's density at sea level, it remains remarkably dense for interstellar space. As these dust particles coalesce, they are forming the seeds of new stars, each collision contributing to the eventual birth of a stellar system. Within this cloud, time unfolds differently than it does on Earth. While our planet circles the Sun in a year, B68's collapse occurs over millions of years. The process is governed by gravity and temperature, with heat slowly leaking away into space. At its heart, B68 is cooling towards equilibrium, where further gravitational collapse will slow to a halt. This cooling process can take upwards of 2 million years, longer than recorded human history. As this happens, the particles inside are not just moving, they are transforming. Chemical bonds begin to form between molecules that were once too energetic to interact, setting the stage for the eventual creation of new stars. The dust grains within B68 vary in size and composition, much like sand on a beach here on Earth. Some particles are as small as micrometers across, while others can be several millimeters wide. These differences matter greatly to the dance occurring within this cloud. Smaller particles tend to collide more frequently due to their greater number, speeding up the process of clumping together into larger structures. Larger grains, however, offer a different role. They serve as nuclei around which gases condense, playing a crucial part in star formation. This intricate balance between particle sizes ensures that B68 is not just collapsing but evolving. As we observe B68 from Earth, it appears dark and impenetrable to our eyes due to the heavy obscuration of visible light by its dense molecular cloud. Yet, this same cloud allows astronomers to study star formation processes with remarkable clarity. Infrared telescopes peer through the darkness, revealing the heat emitted by dust as it warms under gravitational compression. These observations provide a window into the future of our galaxy, a glimpse at how new stars will be born in environments much like B68. Meanwhile, within this cloud, the dance continues without pause or interruption, each collision nudging the particles closer to their ultimate fate. B68's journey is not unique. Countless similar clouds drift through the cosmos, each one a potential nursery for new stars. The process of gravitational collapse and particle coalescence is universal across space and time. Stars are born in this way over billions of years, yet when viewed from the vast expanse of our galaxy, these events seem almost instantaneous. It's a paradoxical reminder that while cosmic processes unfold at an incredibly slow pace, they have been doing so for eons, shaping the universe we see today. As B68 continues to evolve, it will eventually give birth to stars that may one day shine brightly in the night sky, illuminating the path of future explorers and dreamers. In a universe where temperatures can plummet to just fractions above absolute zero in laboratory settings on Earth, one might expect such extremes to be found deep within interstellar space. Yet paradoxically, the coldest known region is not in the void, but right here, inside a lab cooled to 0.1 Kelvin. Though B68 resides in the quiet expanse of space, some 400 light-years away from Earth, its core is not a realm of absolute coldness, but one where internal heat emerges as gravity pulls the dense cloud inward, compressing its mass. This process has been ongoing for roughly 500,000 years, mere seconds in cosmic chronology, and will continue for another 2 million years before reaching equilibrium. The particles within B68 are not frozen statues, but dynamic entities engaged in a slow gravitational dance. Unexpectedly, despite these temperatures plunging to minus 263 degrees Celsius, the cloud's interior glows faintly with heat generated by gravitational collapse, a phenomenon that defies expectations of absolute coldness. Within this globule, the temperature hovers just above absolute zero, yet its interior glows faintly with the heat generated by gravitational collapse. This glow, though dim, is crucial for understanding how stars form from such cold beginnings. For comparison, while B68's core reaches temperatures of minus 230 degrees Celsius, a typical freezer on Earth operates at about minus 18 degrees Celsius, a stark difference indeed. The internal heat generated by this collapse is not enough to warm the cloud, but is sufficient to initiate the formation of stars. Instead of focusing solely on the coldness, consider that the particles within B68 are in motion, their interactions generating a faint glow that signals the onset of star birth. The globule spans an expanse roughly 1 light-year across, hardly vast by cosmic standards, yet immense when compared to the scale of human experience. Within this space, B68 contains approximately 2 solar masses of gas and dust. a concentration that is dense enough to seed star formation, but still sparse in comparison to the air we breathe on Earth. At 10,000 molecules per cubic centimeter, B68's density is extreme for interstellar conditions, yet pales in comparison to the trillions of molecules found in each cubic centimeter of our atmosphere. Imagine a human body entering this frigid cloud. Within moments, the cold would seep through every layer of clothing and skin. Yet, paradoxically, it would be the lack of warmth rather than intense cold that causes harm. Your blood would solidify at such temperatures, leading to rapid death by hypothermia. This highlights the extreme conditions necessary for star formation. B68's particles are so cold they exist on the cusp of quantum mechanics, where classical physics alone cannot fully explain their behavior. As B68 continues its collapse over millions of years, it will gradually cool further still, approaching but never quite reaching absolute zero. This cooling process contrasts with the fiery birth that awaits at the core, where new stars will ignite from the concentrated mass. The paradox of this region is not just in its temperature extremes, but also in its role as a cradle for stellar life within an otherwise barren cosmic landscape. Each dust particle within B68, though isolated and cold, contributes to a future filled with light and energy, reminding us that even in the harshest environments, new beginnings are always possible. Gravity exerts a quiet but persistent influence on Bok Globule B68, a vast cloud of gas and dust that spans approximately 1 light-year across. This gravitational settling began roughly 500,000 years ago, an infinitesimal fraction of the universe's age. Each molecule within this cosmic region is drawn toward its center with a precision akin to the slow drip of sand through an hourglass. At temperatures close to absolute zero, just above -263 degrees Celsius, the molecules in B68 move with minimal kinetic energy, yet their collective motion under gravity creates an intricate dance. The density within B68 reaches around 10,000 molecules per cubic centimeter, which may seem sparse compared to Earth's atmosphere, but is dense for interstellar space. This gradual compression could eventually trigger star formation as the cloud collapses further. While this process unfolds over millions of years, it doesn't proceed uniformly. Variations in local temperature and pressure cause pockets of denser material to form within B68. These regions are primordial nurseries where future stars may emerge from the interstellar dust. The contrast between the slow collapse and the eventual burst of stellar birth highlights nature's paradoxical efficiency. B68's journey is not just a matter of collapsing inward. It also orbits toward the galactic center, a destination governed by the galaxy's gravitational field. This migration can take millions of years, shaped by the complex interplay of forces within the Milky Way. The cloud's path through space is far from direct, winding like a river meandering through valleys. The process of B68 settling under gravity has profound implications for our understanding of star formation. It illustrates how regions in space that appear static to us are actually dynamic systems governed by complex physical laws. As these clouds collapse and stars form, they release energy back into the universe, enriching it with heavy elements produced within their cores. B68's current state is merely one moment in a cycle billions of years long, where cosmic material condenses into stars, which then explode or evolve, dispersing matter once more. This ongoing process shapes not just B68, but entire galaxies over eons. Each molecule's journey toward the center mirrors an ancient and enduring dance of creation and destruction that defines our universe. Gravity's grip on B68 is part of a larger cosmic ballet where every cloud, nebula, and star plays its role. The gentle tug that draws molecules together in B68 also propels stellar winds across galaxies, seeding new clouds with the elements forged in ancient supernovae explosions. This continuous cycle ensures that each generation of stars is built from the remnants of previous ones, a testament to nature's recycling efficiency. The collapse of B68 into denser regions highlights how cosmic processes can be both patient and relentless. Over millions of years, these subtle motions will lead to the formation of new stars within its core. The contrast between this slow accumulation of mass and the explosive birth of stars underscores the delicate balance that governs star formation. As B68 continues its journey toward the galactic center, it becomes part of a larger network of interstellar clouds moving under the influence of gravity. This interconnectedness reveals how our galaxy is not just a collection of isolated regions, but a dynamic system where every cloud affects others, creating a web of interactions that spans vast distances. In this quiet expanse, B68's collapse into denser regions offers insight into the birth of stars and the recycling of cosmic material. Each molecule's journey toward the center mirrors an ancient and enduring dance of creation and destruction that defines our universe. At its heart, Bok Globule B68 is a dense pocket of interstellar dust and gas where particles are packed together at a rate of about 10,000 molecules per cubic centimeter, remarkably crowded for space's typically sparse environment. Yet just beyond this core, the density drops sharply, with the edges of B68 becoming as wispy and translucent as if they were mere shadows cast by the denser center. This gradient is not merely an aesthetic contrast, but a fundamental property that influences how stars are born within such regions. Inside Bok Globule B68's dense heart, gravitational forces pull particles together in a relentless dance, each collision nudging molecules closer to nuclear fusion conditions. Meanwhile, at its edges, where temperatures hover near -263 degrees Celsius, these conditions are far too frigid to sustain any significant chemical reactions or nuclear fusion. The contrast is stark. While the core teems with potential life, the periphery remains a cold and inactive shell. Interestingly, this temperature difference within B68 mirrors the way Earth's oceans change from warm surface waters to freezing depths near the ocean floor. The heart of B68 is not just dense in terms of mass, it's also rich in elements heavier than hydrogen and helium, elements that were forged in earlier generations of stars that have since expired. These heavy atoms are crucial for forming planets, and their concentration here signals that this globule may one day birth a system much like our own solar system. In contrast, the edges, being more diffuse, hold less promise for star formation, but can still serve as reservoirs for future cosmic cycles. The edges also act as protective barriers, shielding nascent stars from harmful radiation and cosmic debris. As we peer into the heart of B68, its dense core stands out against the vast emptiness that surrounds it. The pressure within this region is so intense that it would crush any human body to a fraction of its original size, or one somehow present. Yet outside this compressed center, the space feels more like an open void than a true vacuum, with distances between particles stretching far enough apart for even light to travel unhindered. This contrast in density and emptiness mirrors the way our own lungs expand and contract, filling with air, then expelling it into a much larger surrounding environment. Over its lifetime of about 500,000 years so far, B68 has been gradually collapsing under gravity's pull. The rate at which this collapse occurs is slowing down as it approaches a stable equilibrium. This process, while slow by human standards, is rapid on cosmic timescales. In contrast, the edges of B68 have barely changed in millennia, remaining wispy and untouched by the gravitational forces that shape its center. Notably, these fringes can also provide insights into the initial conditions of star formation before any significant changes occur. However, an unexpected fact emerges. Despite their apparent stability, the outer layers occasionally experience minor disruptions caused by nearby cosmic events, such as passing stars or shock waves from supernovae. The core's dense heart will eventually give birth to several stars over millions of years, while the outer edges remain largely inert. Yet these fringes play a crucial role in shielding nascent stars from harmful radiation and cosmic debris until they are fully formed. This delicate balance between active center and passive periphery is a common theme throughout star-forming regions across the galaxy, each one contributing to the vast network of stellar nurseries that dot the cosmos. The process within B68 also provides a glimpse into how our own sun might have formed billions of years ago in a similar environment. Immersed within Bok Globule B68, a sense of weightlessness prevails as you drift through its vast emptiness. The pressure here is negligible, far less than what you might feel at the top of Mount Everest on Earth. Your body floats effortlessly, each movement slow and deliberate. Were you to stretch out your arm, it would take moments for even the smallest action to register. In this environment, time feels both stretched and compressed. The cold seeps into your bones, not a biting chill like at the coldest reaches of Antarctica, but an all-encompassing freeze that penetrates deep within your cells. At -263 degrees Celsius, molecules vibrate so slowly they are barely distinguishable from stillness. This temperature is closer to absolute zero than any naturally occurring place on Earth. Yet it's here, within B68, that stars will eventually be born. The paradox lies in this. The coldest known region of space contains within its heart the seeds of stellar life. The darkness around you is profound, with light from distant stars barely able to penetrate the dense layers of dust and gas that make up B68's core. Your eyes struggle to adjust, but eventually you can perceive a faint glow, starlight scattered in long arcs across the cloud. This luminescence reveals not only your surroundings, but also the vastness beyond. Were you to turn your gaze toward Earth, it would lie 400 light-years away, an unseeable pinprick of blue from this vantage point. Each cubic centimeter of B68 contains roughly 10,000 molecules, astoundingly dense for interstellar space. Yet in the grand scheme of cosmic density, this is still sparse. Earth's atmosphere at sea level holds more than 1 trillion times as many particles. The emptiness here is so vast that you are surrounded by silence. Sound requires matter to travel, and there is little substance here to carry waves. Thus, any noise you might make would dissipate into the void, unheard even in this immediate vicinity. The cloud's edges begin their gentle slope toward transparency as you move further away from its dense center. Here, particles are more spread out, a less crowded environment compared to what lies deeper within B68. The process of gravitational settling continues, gradually compressing material into denser clumps. Over the next 2 million years, these clumps will coalesce, eventually forming stars. Meanwhile, you float weightlessly in this transitional region, where the balance between emptiness and density is a delicate dance of cosmic forces. Each movement feels isolated, as if time itself has slowed to accommodate the vastness of space around you. As you drift further into B68's periphery, the temperature begins to rise slightly, though it remains bitterly cold by earthly standards. This gradual warming is due to the decreasing density of particles, which allows for a slight increase in molecular activity. The process contrasts sharply with the core, where temperatures approach absolute zero and molecules barely move. Here, you can feel the subtle shift as the cloud structure becomes less uniform, hinting at the dynamic nature of B68's formation. The vastness of space around you is filled with a faint, diffuse glow from distant stars that have been scattered by B68's dense layers. This light provides a rare glimpse into the cosmic neighborhood, revealing the intricate web of starlight that connects this cloud to the rest of the galaxy. Each photon has traveled for hundreds or thousands of years before reaching your eyes, carrying with it stories of stellar evolution and the universe's grand tapestry, forged in stars long since extinguished. Yet here, within B68, you are shielded from much of this light, existing in a realm where darkness reigns supreme. As you continue to float, you notice small particles drifting past you, each one a remnant of the interstellar medium that has been drawn into B68 over millennia. These grains of dust and ice may eventually coalesce into larger structures, contributing to the birth of new stars. The process is slow but relentless, with gravity gradually pulling these particles together. In this environment, time stretches out, each moment a fleeting pause in an ongoing cosmic dance. 1 billion years ago, in a region of space far from Earth's familiar skies, Bok Globule B68 was not isolated, but part of a broader cosmic narrative. Just beyond its borders lay the stellar nursery known as B67, a bustling site of star formation. As B68 began to coalesce under its own gravity, it felt the subtle pull of B67's gravitational field. This influence shaped not just its structure, but also its evolutionary timeline. Every dust particle in B68 was drawn inward by invisible threads stretching across the void. A dance of cosmic proportions played out over millions of years. The temperature within B68 dropped to an astonishing -263 degrees Celsius, close to absolute zero, as it settled into its current form. This chilling environment is far removed from the fiery furnaces where stars ignite. Yet in this cold and quiet space, the seeds of new stellar life are slowly taking root. The core at the heart of B68, dense with molecular hydrogen and other elements essential for star formation, mirrors the conditions that eventually gave rise to our Sun. This region's temperature is so low it approaches the coldest known temperatures in the universe, achieved only through sophisticated cooling techniques on Earth. Such extreme cold within B68 ensures that chemical reactions proceed at a snail's pace, preserving the pristine conditions needed for star formation. As we peer into this ancient past, we see a cosmic dance unfold between B67 and B68. The particles in these clouds were once part of the same interstellar medium, drifting together until they found themselves separated by just a few light years. This distance, minuscule on the scale of the universe, allowed for their independent yet interconnected evolution. Over time, B68's gravitational settling has slowed down as it approaches a stable equilibrium. The process, which began about 500,000 years ago, is expected to take another 2 million years to complete, a momentary blip in cosmic history. The core of B68, with its density of 10,000 molecules per cubic centimeter, seems dense by interstellar standards, but is still far less crowded than Earth's atmosphere at sea level. Yet even such sparse concentrations exert a significant gravitational influence. This gravitational pull not only draws the particles toward the center, but also shapes the overall structure of B68. The cloud's edges are thinner and more translucent, allowing distant stars, light to pass through and reveal its internal complexity. Meanwhile, nearby B67 continues to birth stars, each one carrying within it a trace of the cosmic connection that brought them into being. In this environment, where sound cannot travel due to the lack of molecules, the only communication is through electromagnetic radiation, light and radio waves that traverse the void unimpeded by any medium. The particles in B68 are in constant motion, colliding gently as they spiral toward the center. These collisions are rare but significant, each one contributing to the gradual buildup of mass at the cloud's core. This process is akin to a cosmic snowball rolling downhill, gathering more material with each step. Despite the extreme cold and sparse density, the particles within B68 are engaged in an intricate dance that will eventually culminate in the birth of new stars. As we reflect on this ancient scene, it becomes clear how intertwined our Sun's origins are with these distant cosmic events. The iron in your blood was forged in stars like those forming near B67 and B68 billions of years ago. These stellar nurseries are not just distant phenomena, they are the cradles of elements that make life possible. The particles within B68, now slowly coalescing into stars, carry with them the potential for new solar systems, planets, and perhaps even life. This connection between our origins and the far reaches of space underscores the profound interconnectedness of all things in the cosmos. In Bok Globule B68, a process unfolds that takes place at an almost imperceptible pace. Atomic particles within this cloud are slowly converting dust into molecules, one by one, over millions of years. Each collision between these tiny specks is both a beginning and an end, a new molecule born from the union of simpler elements. Every time two atoms collide in B68's cold embrace, they form bonds that hold them together for eons. This process mirrors the slow accumulation of sediment in riverbeds on Earth, where grains of sand build up to create mountains over millennia. Yet unlike rivers or glaciers, which are visibly dynamic, these transformations within B68 occur at temperatures so low that molecular motion is barely detectable. As the cloud settles under gravity, the dust particles move inward toward the center, creating regions where density increases. These denser areas act like seeds for future stars, gradually increasing in temperature and pressure until they reach critical points. The process is akin to the way snowflakes accumulate on a mountainside before avalanches occur. Each additional particle adds weight and stress that could trigger significant changes. Yet at this moment, B68 remains stable, its particles gently settling into place like grains of sand after an earthquake. Each molecule formation within B68 is not just a local event, but part of a vast network of interactions. The cloud's interior is teeming with these tiny collisions, each contributing to the eventual coalescence of material that will one day become stars. In contrast to Earth's bustling molecular exchanges in our atmosphere, where reactions happen at lightning speed, B68 operates in near silence. Yet this silence belies a profound activity, a universe-scale construction site where materials are meticulously arranged for future stellar birth. Within Bok Globule B68, the process of converting dust into molecules is not just about creating more complex structures. It's also about rearranging the building blocks of space itself. As gravity draws particles together, their movement influences surrounding regions, causing a cascade effect that spreads throughout the cloud. This intricate interplay between forces and matter ensures that B68 continues to evolve, step by tiny step, toward its eventual destiny as a stellar cradle. The temperature within B68 hovers around 4 degrees above absolute zero. At this near absolute zero state, the kinetic energy of particles is reduced to almost nil. This extreme cold ensures that molecular motion remains minimal, yet it does not stop the ongoing dance of particles. The molecules formed here are incredibly stable in these conditions, their bonds unbroken by thermal agitation. In a paradoxical twist, this frigid environment allows for precise and reliable reactions, ensuring each collision results in successful bonding. This stability contrasts sharply with the turbulent, high-energy environments found elsewhere in the universe. Bok Globule B68 is not just a passive observer of cosmic time. It plays an active role in shaping the universe around it. The molecular processes within this cloud are fundamental steps in the long journey from diffuse gas to fully formed stars. Each collision and bond formation represents progress toward the creation of celestial bodies that will one day illuminate the darkness with their radiant light. Over millions more years, B68 will continue its slow transformation, inch by molecule, until it becomes a vibrant nursery for newborn stars. The density within B68 continues to rise as gravitational settling pulls particles toward the center, creating regions where dust clumps together. These denser areas act like seeds for future stars, gradually increasing in temperature and pressure until they reach critical points. The process is akin to the way snowflakes accumulate on a mountainside before avalanches occur. Each additional particle adds weight and stress that could trigger significant changes. Yet at this moment, B68 remains stable, its particles gently settling into place like grains of sand after an earthquake. Each molecule formation within B68 is not just a local event, but part of a vast network of interactions. The cloud's interior is teeming with these tiny collisions, each contributing to the eventual coalescence of material that will one day become stars. In contrast to Earth's bustling molecular exchanges in our atmosphere, where reactions happen at lightning speed, B68 operates in near silence. Yet this silence belies a profound activity, a universe-scale construction site where materials are meticulously arranged for future stellar birth. Within Bok Globule B68, the process of converting dust into molecules is not just about creating more complex structures. It's also about rearranging the building blocks of space itself. As gravity draws particles together, their movement influences surrounding regions, causing a cascade effect that spreads throughout the cloud. This intricate interplay between forces and matter ensures that B68 continues to evolve, step by tiny step, toward its eventual destiny as a stellar cradle. The temperature within B68 hovers around -263 degrees Celsius, just above absolute zero. This extreme cold ensures that molecular motion remains minimal, yet it does not stop the ongoing dance of particles. The molecules formed here are incredibly stable in these conditions, their bonds unbroken by thermal agitation. In a paradoxical twist, this frigid environment allows for precise and reliable reactions, ensuring each collision results in successful bonding. This stability contrasts sharply with the turbulent, high-energy environments found elsewhere in the universe. Bok Globule B68 is not just a passive observer of cosmic time. It plays an active role in shaping the universe around it. The molecular processes within this cloud are fundamental steps in. In the heart of Bok Globule B68, a region of near-total silence prevails. Sound cannot propagate through the tenuous gas that fills this space, and temperatures drop to as low as -263 degrees Celsius. close to absolute zero. Each molecule within B68 drifts apart from its neighbor by an average distance of about 1/1000th of a millimeter, comparable to imagining a grain of sand floating in a vast stadium filled with air. This sparse environment means any vibration from a passing star would be lost in the immense void. Yet electromagnetic radiation, like radio waves, can travel freely through this vacuum of space, carrying information across billions of light years without interruption. The density within B68 is about 10,000 molecules per cubic centimeter, a number that seems dense by cosmic standards, but pales in comparison to Earth's sea-level atmosphere, which contains 10 quintillion times more particles. B68's gravitational settling process began approximately 500,000 years ago, an imperceptibly brief span when viewed against the backdrop of cosmic time. Gravity gradually pulls dust particles closer together in intricate patterns, each molecule tracing paths determined by its neighbor's movements and the overall structure of the globule. This slow dance of matter continues undisturbed, with no sound to accompany it. Imagine floating within B68. The temperature would feel unbearably cold, yet silence reigns, no rustling winds or distant hums. The only signs of activity come from faint infrared emissions leaking through the dense molecular cloud, revealing the slow dance of matter under gravity's gentle pull. This scene, though tranquil and serene, holds within it the promise of new stars forming over millions more years in this quiet expanse. Despite the silence, B68's environment is far from static. The molecules within do not float aimlessly. Instead, they move in precise, calculated orbits determined by their mutual gravitational attraction. This delicate balance ensures that any disturbance, such as a nearby supernova explosion, propagates through the cloud only as subtle shifts in temperature and density rather than audible sounds. Each particle follows its own unique path, a dance choreographed by gravity over cosmic timescales. In this environment, time stretches infinitely. The collapse of B68 is expected to take millions more years, during which new stars will gradually form from its dense core. Each particle within the globule follows its own unique trajectory, a dance orchestrated by gravity across vast cosmic epochs. This slow, deliberate movement contrasts sharply with the fleeting nature of human perception, where moments pass in an instant. Yet for B68, each moment is a step toward its eventual transformation into stars, a process that will unfold over periods beyond our comprehension. In this frigid and silent realm, the gravitational settling of B68 proceeds with an almost imperceptible slowness. The cloud's collapse is a delicate process, where each dust particle navigates its path through the tenuous gas with painstaking precision. This slow dance of matter unfolds over millions of years, a timescale that dwarfs human lifespans and even historical epochs on Earth. The temperature within B68 hovers near absolute zero, but this extreme cold does not render it lifeless. Instead, it is a stage for the quiet drama of star formation. The dust grains within the cloud are not passive actors. They are engaged in an intricate ballet, colliding and coalescing into larger structures. These collisions, though rare by human standards, are crucial for the eventual birth of stars. Each encounter between particles adds infinitesimal amounts of mass to nascent stellar seeds, gradually building up the material that will one day ignite into brilliant beacons. This process is akin to a cosmic hourglass, where time itself seems to slow down. While we might perceive minutes or hours as significant units of time, in B68, these periods are mere blinks compared to the eons it takes for a star to form. The cloud's collapse is governed by the delicate balance between gravity pulling inward and internal pressure pushing outward. This equilibrium ensures that the formation of stars proceeds at a measured pace, allowing each particle to find its place in the cosmic architecture. As we observe B68 from Earth, 400 light-years away, it appears as a dark silhouette against the backdrop of distant stars. Yet this darkness is not an absence, but rather a profound presence, a testament to the dense molecular cloud that shields us from direct view of its inner workings. The very opacity that obscures our sight highlights the complexity and richness hidden within B68's depths. In the quiet expanse of space, Bok Globule B68 presents an enigma wrapped in polarized light. Instruments detect a subtle twist in the electromagnetic waves as they bend around dense regions within this cosmic cloud. This phenomenon, known as gravitational lensing, occurs when gravity warps spacetime, bending light paths much like a magnifying glass might focus sunlight. The intensity of this bending provides astronomers with clues about the mass and distribution of matter inside B68. Each photon traveling through these dense zones encounters a labyrinth of gas and dust particles, their trajectories altered as they navigate this cosmic obstacle course. This warping effect is not instantaneous. It takes time for light to be redirected by gravitational forces within the cloud. For an observer on Earth, the delay in detection can be measured in fractions of a second, though these delays accumulate over 10 parsecs, revealing the true depth and structure of B68's interior. Incredibly, this bending also serves as a cosmic clock, helping scientists estimate how long it has been since B68 began its gravitational collapse. Imagine a beam of light passing through a dense forest, where trees act like massive particles in space. Just as sunlight might weave between tree trunks, photons twist and turn around the molecular cloud's densest regions. The temperature inside B68 averages minus 263 degrees Celsius, close to absolute zero. Yet, despite this extreme cold, the process of light bending through B68 is a dynamic one, with each photon tracing unique paths influenced by the unseen architecture within. Notably, these photons also carry information about the speed at which they are traveling as they pass through different densities, providing additional insights into the cloud's internal dynamics. Within these cold and dark zones, polarized light reveals more than just density. It illuminates the very process of star formation. The twisting photons carry information about magnetic fields threading through B68's dense core, where stars are poised to emerge. These magnetic fields play a crucial role in the collapse of molecular clouds, by channeling material into nascent stellar disks. The light bending reveals these intricate patterns, acting as cosmic X-rays for the unseen structures within. Remarkably, the same forces that cause light to bend around B68 also affect Earth's weather systems. Gravitational lensing is akin to how mountains can influence airflow on our planet, redirecting winds and clouds in predictable ways. In space, however, this effect operates across scales incomprehensibly vast. For B68, the gravitational forces at play are so powerful that they warp light paths over distances measured in light years. The bending of light around dense regions within the cloud is a testament to the immense forces shaping not just B68, but entire galaxies. An unexpected twist. While these forces bend light outward, they can also create shadow-like effects where no light escapes, revealing dark zones that are crucial for star formation. As we observe the polarized light twisting through B68, it becomes clear that this phenomenon is more than just an optical illusion. It's a profound reminder of the interconnectedness of cosmic processes. The same gravitational forces at work here have influenced star formation throughout the universe's history. In the heart of this cloud, stars are slowly being born, each one contributing to the ongoing cycle of stellar evolution in our galaxy. Light continues its journey through B68, bending and revealing stories far older than humanity itself, a quiet dance of photons that narrates the birth of stars. Bok Globule B68 exemplifies the star formation processes that occur across galaxies. Within its approximately 1 light-year span, gravity pulls together gas and dust particles, initiating a collapse that began roughly 500,000 years ago. At its core, B68's density reaches about 10,000 molecules per cubic centimeter, an environment densely packed compared to interstellar space, but still far less dense than Earth's atmosphere at sea level. This compression increases the likelihood of collisions between particles, gradually building up the mass needed for star formation. Despite this high density, it remains significantly less dense than Earth's atmosphere, which contains 1 trillion times more molecules per cubic centimeter. Yet in cosmic terms, B68's density is sufficient to initiate nuclear fusion and spark new stars. The gravitational settling within B68 mirrors processes happening in countless similar clouds across galaxies. Across our Milky Way alone, thousands of molecular clouds are undergoing this same process, each contributing to the continuous creation of stellar systems. This cycle has been repeating for billions of years, since the earliest stars flickered into existence shortly after the Big Bang. As B68's collapse progresses over millions of years, it will fragment into smaller clumps, some of which may coalesce into individual stars or multiple star systems. These fragments could ignite nuclear fusion, producing new stars that will contribute to the ongoing cycle of stellar birth and death. This fragmentation process is akin to breaking apart a large ice block into smaller chunks. Each piece can then melt at its own pace. B68's temperature within this process can drop as low as -263 degrees Celsius, close to absolute zero. This extreme cold is crucial for star formation, as it slows molecular motion, allowing gravity to take control. Despite these frigid conditions, B68 remains far from static. Gas molecules continue their slow dance of collisions and coalescence, gradually forming larger structures that can eventually ignite into stars. Iron in your blood was forged in the remnants of massive stars that exploded as supernovae around 13 billion years ago, shortly after the Big Bang. These elements are carried forward through the cosmic cycle, being incorporated into new stars like those potentially forming within B68. This continuous recycling and repurposing of stellar material is a fundamental aspect of how galaxies evolve over time, shaping the universe we observe today. Each star that forms from B68's fragments will carry this legacy forward, contributing to the ongoing narrative of cosmic chemistry across the galaxy. Within B68, the temperature can plummet to as low as minus 263 degrees Celsius, close to absolute zero. This extreme cold is crucial for star formation, as it slows molecular motion, allowing gravity to take control. Despite these frigid conditions, B68 remains dynamic. Gas molecules continue their slow dance of collisions and coalescence, gradually forming larger structures that can eventually ignite into stars. B68's collapse process reveals a fascinating connection between its formation and the broader cycle of star birth across galaxies. Each fragment within B68 has the potential to become part of this grand cosmic recycling process, where elements from dead stars are repurposed in new stellar systems. This continuous cycle not only shapes individual clouds like B68, but also influences the overall structure and evolution of entire galaxies. The density within B68 is about 10⁴ molecules per cubic centimeter, which is extremely dense for interstellar space, but still incredibly sparse compared to Earth's atmosphere at sea level. Despite this low density, B68 contains roughly 2 solar masses of gas and dust, with the potential to form several stars over time. This demonstrates how even in environments that seem empty by human standards, there can be vast amounts of material available for star formation. B68's location, approximately 400 light-years from Earth, provides astronomers with a unique vantage point to study star formation processes up close. The cloud is large enough, about 1 light-year across, to allow detailed observations of the entire collapse process. This proximity and size make B68 an invaluable laboratory for understanding how stars are born, offering insights into the conditions that lead to stellar birth in other parts of our galaxy. As B68 continues its gravitational settling over millions of years, it will approach a stable equilibrium after about 2 million years of collapse. During this time, the cloud's internal structure will evolve, with denser regions forming cores where stars are likely to form. This gradual process highlights how star formation is not instantaneous, but rather unfolds over vast timescales, illustrating the patient nature of cosmic processes. Each fragment within B68 has the potential to become part of a new stellar system, carrying forward elements from massive stars that exploded as supernovae around 13 billion years ago. This cycle not only shapes individual clouds like B68, but also influences the overall structure and evolution of entire galaxies. In the quiet expanse of space, Bok Globule B68 maintains a delicate balance, its dense core slowly coalescing under the pull of gravity. At approximately -263 degrees Celsius, this cosmic cloud is one of the coldest known regions in our galaxy. The gravitational settling within B68 has been ongoing for about 500,000 years, an infinitesimal fraction of the universe's age. Yet this tranquility will soon be disrupted by a nearby supernova explosion, sending shockwaves through the cloud that could alter its fate. The shockwave from the supernova travels at thousands of kilometers per second, compressing and heating B68's gas and dust particles as it passes. This compression can trigger star formation within the globule, potentially leading to the birth of several new stars. The energy released by a single supernova is equivalent to that of trillions of nuclear bombs detonating simultaneously. Despite this immense power, the shockwave's effects are not uniform across B68. Its dense core remains relatively undisturbed due to its higher density and gravitational stability. In contrast, the cloud's edges, less tightly bound by gravity, will experience more significant changes. As the supernova shockwave interacts with B68, it creates a series of compression waves that ripple through the molecular cloud. These waves can trigger localized heating, causing some dust particles to collide and stick together, forming larger aggregates. This process is akin to how water droplets merge in clouds on Earth before precipitation occurs. However, unlike Earth's atmosphere, where collisions are frequent due to higher density, B68's low particle density means these events happen at a much slower pace. Yet, even this slow process can lead to the formation of new stars over millions of years. The temperature within B68 rises slightly in response to the shockwave, but it remains incredibly cold by human standards, still close to absolute zero. This extreme cold means that chemical reactions proceed at a snail's pace, if they occur at all. The molecules within B68 are barely vibrating, and any interaction between particles is rare. Yet, this environment is far from lifeless. The shockwave introduces new dynamics, causing some regions of B68 to become slightly warmer and more reactive than others. This localized heating can lead to the formation of complex molecules that might otherwise take much longer to develop. The supernova's impact on B68 also affects its long-term stability. The shockwave could accelerate the collapse of certain parts of the cloud, potentially leading to an increase in star formation rates within those regions. This acceleration contrasts with the slow and steady gravitational settling that has been occurring for millennia. While some areas may see rapid changes, others will remain relatively stable, continuing their gradual descent toward equilibrium. Over time, these differences could lead to a more diverse array of stellar systems forming within B68. In the aftermath of the supernova event, astronomers on Earth will observe subtle changes in B68's structure and composition. These shifts may take years or even decades to become apparent, as the shockwave continues to propagate through the cloud. The effects of this cosmic disturbance will ripple outward, influencing not just B68, but also its neighboring regions within the galaxy. In the quiet expanse of space, gravity warps spacetime around Bok Globule B68 through a measurable effect known as gravitational lensing. Near its core, where the density of gas and dust reaches up to 10,000 molecules per cubic centimeter, spacetime curves ever so slightly under the relentless pull of gravity. Each particle within B68 contributes to this collective effort that subtly stretches spacetime around it. Though small compared to galaxies or black holes, B68's mass is substantial enough to create measurable effects. The temperature within B68 can drop to nearly -263 degrees Celsius, just 10 Kelvin above absolute zero, creating an environment where molecular motion slows dramatically. Over millions of years, B68 will continue to settle under gravity's influence until it reaches a stable equilibrium after about 2 million years of collapse. This gradual deceleration marks a phase in the cloud's evolution where it transitions from diffuse interstellar medium into dense regions capable of forming stars. The cooling process within B68 is remarkable, with temperatures dropping close to absolute zero, highlighting the extreme conditions necessary for star birth. As particles cluster together under gravity's influence, they heat up slightly through collisions, marking a subtle shift in this otherwise frigid environment. This delicate balance between cooling and heating is key to understanding how such clouds eventually give rise to new stars. The gravitational settling process not only shapes B68, but also influences the surrounding interstellar medium, creating ripples that extend far beyond its boundaries. During the collapse of B68, which began roughly 500,000 years ago, an unexpected phenomenon occurs. Despite the cooling temperatures, small pockets within the cloud experience brief spikes in temperature due to shock waves caused by nearby cosmic events. These transient heat sources are crucial for initiating chemical reactions that eventually lead to star formation. Gravity's influence on B68 extends far beyond its immediate vicinity, subtly affecting the fabric of spacetime in its surroundings. As matter within the globule coalesces and compresses, it creates a gravitational well that bends light paths from distant stars passing nearby. This bending is not uniform. Instead, it mirrors the varying density gradients within B68, revealing the cloud's internal structure through subtle distortions. Astronomers can use these lensing effects to map out the distribution of mass and understand how different regions contribute to the overall gravitational field. The collapse of B68 began roughly 500,000 years ago, a brief period in cosmic terms, but essential for understanding star formation. This timeline is a fraction of the universe's age, yet it encapsulates the intricate processes that lead to stellar birth. The density within B68, about 10,000 molecules per cubic centimeter, contrasts starkly with Earth's atmosphere at sea level, which contains around 10 billion times more molecules in the same volume. This comparison underscores just how sparse interstellar space is compared to our familiar environment. Astronomers can also observe distant light sources that lie behind or near B68, revealing slight curvatures in their paths due to gravitational lensing. These observations provide indirect but powerful evidence of gravity's role in shaping not just the globule itself, but also its interaction with the broader cosmic environment. This interplay between local and universal scales highlights how even small regions like B68 play crucial roles in understanding larger cosmological phenomena. Moreover, as particles within B68 continue to settle under gravitational forces, they generate minute amounts of heat through collisions. Despite the near absolute zero temperatures, this internal heating is significant enough to alter the thermal balance within the cloud. These temperature fluctuations are minuscule but critical for initiating the chemical reactions that eventually lead to star formation. The cooling process is so efficient in B68 that it approaches conditions found only in specialized laboratories on Earth, where scientists simulate similar environments to study fundamental physics. In essence, gravity's warping of spacetime around B68 is both a local and cosmic event. It reflects the delicate balance between cooling and compression, highlighting how even slight variations can have profound implications for star formation. This intricate dance of forces continues over millions of years, gradually transforming what was once a diffuse cloud into a nursery for new stars. Each step in this process contributes to our understanding of how the universe assembles. In the heart of Bok Globule B68, a region teeming with gas and dust particles at temperatures close to absolute zero, lies an intricate process that will culminate in the birth of stars. As it continues its gravitational collapse, B68's core contracts under immense pressure, compressing its contents into denser forms. At this moment, the density within the cloud reaches approximately 10,000 molecules per cubic centimeter, a stark contrast to Earth's atmosphere at sea level, which boasts a staggering 100 billion times more molecules in the same volume. This density difference underscores just how sparse space can be when compared to our familiar terrestrial environments. As B68's core continues to compress over the next 2 million years, it will approach an equilibrium where gravitational forces balance internal pressure. The collapse of B68 is a process that defies immediate observation, yet is as predictable as any natural event on Earth. Imagine if you could watch ice form in a freezer from a distance. Initially, nothing seems to happen, but gradually, the water molecules arrange themselves into an ordered crystal lattice. Similarly, within B68, individual atoms and dust particles are slowly organizing under gravity's pull. This organization is not static, rather. It is a dynamic equilibrium where slight changes ripple through the cloud like ripples on a pond after a pebble has been thrown in. By the time B68 fully collapses into a protostar, this delicate dance of molecules will have taken place over an incredibly long timescale, with each step in the process being meticulously calculated by cosmic forces. As we peer deeper into B68's future, the cloud begins to heat up due to its own gravitational energy. This internal warmth is a stark contrast to the frigid exterior that has been its hallmark for millions of years. The temperature at the core can rise to nearly minus 250 degrees Celsius, close to absolute zero, but still warmer than the coldest known laboratory on Earth. Meanwhile, outside this central region, temperatures remain extremely low, approaching minus 263 degrees Celsius. This gradient creates a unique environment where different physical processes occur at varying scales and speeds. Within this temperature range, the gas molecules move with minimal kinetic energy, barely interacting except through gravitational attraction. When B68 fully collapses into a protostar, it marks the beginning of an entirely new phase in its cosmic life cycle. The collapse will have taken nearly 2 million years, a time frame that stretches beyond human comprehension. Once this stage is complete, the newborn stars within B68 will begin to emit radiation across a wide spectrum of frequencies, from infrared to X-rays. This energy release will illuminate their surroundings, transforming what was once an opaque molecular cloud into a radiant stellar nursery visible from Earth. The light from these newly formed stars will travel through space at the speed of light, eventually reaching us in the form of photons that can be detected by telescopes on Earth and in orbit. Within B68's collapsing core, chemical reactions are beginning to occur more frequently as temperatures rise slightly above absolute zero. These reactions involve the formation of complex molecules from simpler atomic constituents. While these processes happen at an extremely slow pace compared to what we experience on Earth, they are crucial for star formation. The iron and silicon accumulating in the central region will eventually contribute to the structure of young stars. This process is not unique. Similar transformations have occurred throughout the galaxy, leading to the diverse array of celestial bodies we observe today. Once B68 has fully collapsed into a protostar, it will begin to radiate energy outward, pushing away surrounding gas and dust. This radiation pressure can create cavities or bubbles in the molecular cloud, allowing light from the nascent stars to escape more freely. Over time, these structures may influence nearby star formation by providing seeds for new stellar systems. The process of gravitational collapse and subsequent radiation emission is a fundamental mechanism that shapes galaxies across cosmic history. In this way, B68's transformation contributes not only to its own evolution, but also to the broader narrative of how stars form and interact within our galaxy. In the heart of Bok Globule B68, a striking contrast appears. Despite being colder at its core, this region glows brighter than its edges. This anomaly arises from how light behaves in dense environments within the cloud. At minus 263 degrees Celsius, just 10 Kelvin above absolute zero, the particles here are so cold they nearly cease motion entirely. Paradoxically, it is this extreme cold that intensifies light scattering. The denser core reflects more starlight back toward us than the less crowded edges. Imagine drifting through B68 from its heart to its periphery. As you move outward, The light would dim not because the particles are less reflective, but due to fewer molecules to scatter incoming radiation. This phenomenon mirrors Earth's blue sky, where shorter wavelengths of sunlight scatter more efficiently. B68 contains about 10,000 molecules per cubic centimeter, a density that might seem sparse compared to Earth's atmosphere at sea level. Yet for interstellar space, this is remarkable. Each molecule in B68 represents a fragment of cosmic history, having formed from the remnants of ancient supernovae. These particles are now slowly coalescing under gravity's pull, each one contributing to the potential birth of new stars. The process of gravitational settling within B68 began roughly 500,000 years ago, an eye blink in cosmic terms, but still long enough for significant changes to occur. As the cloud collapses, its central regions heat up slightly due to compression, making them appear brighter against the colder, less dense edges. This heating is minimal. The core temperature remains close to absolute zero, yet it suffices to alter visibility. B68's density at its center reaches 10 molecules per cubic centimeter, a density that would be considered nearly empty in Earth's atmosphere, but marks a crucial point for star formation. The iron in your blood was forged in the heart of an ancient supernova, and similar processes are now occurring within B68. Each particle collision here could lead to the creation of new elements or even entire stars over billions of years. B68's journey is part of a broader cosmic narrative where interstellar dust clouds across galaxies collapse into stars through gravitational settling. This process, slow yet inevitable, connects us to the distant past and future of our universe. As we observe B68, we witness not just a cloud, but an ongoing chapter in the story of how the cosmos constructs itself from ancient debris. Each particle collision could be the seed for new stellar systems, linking this remote region to the vast network of stars that dot the galaxy. B68's core not only glows brighter due to increased scattering, but also because it acts as a lens, focusing light from distant stars in an effect known as gravitational microlensing. This phenomenon occurs when the gravity of B68 bends and magnifies the light paths of more distant objects behind it. While imperceptible to human eyes, this subtle bending allows astronomers on Earth to study the internal structure of B68 with greater precision. This lensing effect reveals that the density variations within B68 are not uniform but structured in layers, much like the rings of a tree. Each layer represents different stages of collapse and particle interaction. The outer edges, less dense, allow more light through, while the central regions act as natural magnifying glasses for distant starlight. This intricate pattern is a testament to the delicate balance between gravity pulling particles inward and their tendency to scatter radiation outward. As B68 continues its slow journey toward becoming a stellar nursery, this lensing effect will play an increasingly important role in understanding how stars form within such clouds. The process of gravitational collapse amplifies these light patterns, offering astronomers valuable insights into the internal dynamics at work. This interplay between light and matter, so finely tuned by gravity, underscores the complexity of star formation across the universe. In the heart of Bok Globule B68, a vast cloud of gas and dust spans approximately 1 light-year across. Gravity exerts its subtle influence on each particle within this cosmic nursery. At -263 degrees Celsius, close to absolute zero, these particles are not frozen in time, but engaged in an intricate dance dictated by gravitational forces. This process began roughly 500,000 years ago, a brief moment in the universe's timeline, yet it marks the beginning of star formation within this cloud. Each molecule within B68 moves with precision, their trajectories influenced by gravity's pull, gradually coalescing into denser regions. The density here is about 10,000 molecules per cubic centimeter, an extraordinary figure given its vastness in space, yet still sparse compared to Earth's atmosphere at sea level, where the number of molecules reaches approximately 1 quintillion per cubic centimeter. This contrast highlights the paradoxical nature of interstellar space. While seemingly empty, it harbors regions dense enough to fuel star birth on a cosmic scale. As these particles settle under gravity's pull, they trace out paths that are not random but ordered by gravitational forces. The cloud's edges, once more diffuse, begin to solidify into a denser core. This gradual shift towards equilibrium reflects the delicate balance between chaos and order in the cosmos. Over time, this settling process will shape B68 from its current sprawling form into a dense hub of future stars, each particle contributing to the eventual formation of stellar bodies. In the heart of B68, light from nearby stars is heavily obscured by the cloud's thick molecular veil. Yet, through careful observation using polarized light detection methods, astronomers can peer inside this cosmic cocoon. This technique reveals not just static images, but dynamic processes at play, dust particles slowly coalescing into larger structures. What we witness here is a snapshot of time itself. Billions of years ago, conditions similar to those in B68 existed throughout the galaxy, birthing countless stars that now light up our night sky. As gravity continues its subtle dance within B68, it sets the stage for future stellar life. This cloud's transformation from diffuse dust to concentrated star nurseries is a testament to the intricate processes at work on cosmic scales. Each particle in this slow settling contributes to the recycling of heavy elements throughout the galaxy, an ongoing cycle that has been shaping the universe since its inception. The journey within B68 is not just about forming stars, but also about creating the elements that make life possible, ensuring that each new star carries the legacy of earlier generations of cosmic bodies. Within this cold and dense environment, sound cannot travel due to the lack of air pressure, yet light and radiation can traverse freely through the vacuum. This dual nature of B68, both opaque to visible light and transparent to electromagnetic waves, enables astronomers to study its interior in unprecedented detail. The particles within B68 are not merely passive participants, but active agents in a grand cosmic recycling process, where elements forged in ancient supernovae are now being repurposed into new stars. This slow settling of dust under gravity's pull is a quiet yet powerful engine that drives the chemistry of galaxies, transforming the remnants of past stellar deaths into the seeds of future starbirths. Im Start, Limburg. In the heart of Bok Globule B68, an intricate process unfolds where gravity gently pulls together gas and dust particles, initiating a collapse that began roughly 500,000 years ago. This cloud spans approximately 1 light-year across, yet despite its vast size, it is incredibly dense at its core, containing around 10 molecules per cubic centimeter, remarkably crowded for the typically sparse environment of interstellar space. The temperature within B68 can drop to as low as -263 degrees Celsius, close to absolute zero, creating conditions that are nearly impossible on Earth. This extreme cold is crucial for the formation of complex molecules and dust grains that will eventually seed new star systems. These particles, once formed, are shielded from ultraviolet radiation by the surrounding gas and dust, allowing them to coalesce into larger structures. The recycling of heavy elements within B68 plays a pivotal role in galactic chemistry. The dense core acts as both a collector and distributor of these materials, ensuring that new stars form with the enriched material from older ones. Each molecule within B68's core is not just an isolated entity, but part of a vast network, contributing to the ongoing creation and evolution of galaxies. This process highlights how conditions at opposite extremes, extreme heat in stellar interiors and extreme cold in interstellar clouds, are both necessary for life's building blocks to be formed. The journey of these elements through space is influenced by magnetic fields, shockwaves from supernovae, and even the gentle pull of nearby galaxies. As B68 continues its gravitational collapse, it will eventually form several stars over time, each carrying forward the legacy of older stars that have already contributed to enriching interstellar space. The recycling process within B68 is slow but steady, much like the quiet ticking of a cosmic clock. In 1 billion years, these newly formed stars may themselves be surrounded by their own protoplanetary disks, continuing the cycle of star formation and enrichment. This intricate dance of matter underscores how interconnected everything in the universe truly is, illustrating our place within this grand, ongoing cosmic narrative. Within B68's dense core, temperatures drop to an astounding -263 degrees Celsius, close to absolute zero. This cold environment contrasts sharply with the fiery cores of stars where new elements are forged. Yet paradoxically, this extreme cold facilitates the formation of complex molecules and dust grains by allowing atoms to slow down enough to bond into more intricate structures. These particles can survive here because they are shielded from ultraviolet radiation by the surrounding gas and dust, allowing them to coalesce into larger structures. This protection ensures that these molecules will be ejected back into space as part of B68's gravitational collapse. The process within B68 illustrates how conditions at opposite extremes, extreme heat in stellar interiors and extreme cold in interstellar clouds are both necessary for life's building blocks to be formed. The journey of these elements through space is influenced by specific magnetic field strengths. Shockwaves from supernovae with energies up to 1045 joules, and even the gentle pull of nearby galaxies exerting gravitational forces equivalent to billions of solar masses. Each molecule within B68's core contributes to the ongoing creation and evolution of galaxies. This intricate dance of matter underscores how interconnected everything in the universe truly is, illustrating our place within this grand, ongoing cosmic narrative. A surprising fact is that some molecules formed in such cold conditions can travel vast distances before being incorporated into new stars or planets, potentially influencing the chemical composition of distant systems. Bok Globule B68 contains roughly 2 solar masses of gas and dust, with the potential to form several stars over time. The density within B68 is about 10 molecules per cubic centimeter, which is extremely dense for interstellar space, but still sparse compared to Earth's atmosphere at sea level. This vast emptiness contrasts with the crowded conditions of Earth's surface, where every breath contains millions more particles than B68. The gravitational settling process can slow down as the globule approaches a stable equilibrium after about 2 million years of collapse. Despite its sparse nature in cosmic terms, B68's density is crucial for the formation and recycling of heavy elements back into space. In the heart of Bok Globule B68, a region teeming with gas and dust particles at temperatures close to absolute zero, lies an intricate process where magnetic fields guide cosmic rays through its dense interior. These fields are not uniform but twist and turn as they interact with the cloud structure, influencing the paths of charged particles. At -263 degrees Celsius, this region approaches a state of near total silence. Sound cannot propagate in the vacuum, yet electromagnetic radiation travels freely, revealing the subtle twists in polarized light as it bends around dense zones within B68. This phenomenon provides astronomers with insights into how magnetic fields shape star formation processes on galactic scales. Comparing the scale of B68 to a human cell reveals an astonishing disparity. While B68 spans approximately 1 light-year across, containing roughly 2 solar masses of gas and dust, a single human cell is far smaller, yet contains complex structures like mitochondria. The density within B68 is about 10,000 molecules per cubic centimeter, remarkably crowded for interstellar space, but still sparse compared to Earth's atmosphere at sea level. At the core of B68, gravitational settling causes particles to slowly coalesce into denser regions. This process, which began roughly 500,000 years ago, is a mere blink in cosmic terms. The density gradients within B68 create a contrast between its dense heart and more diffuse edges, illustrating how gravity's pull varies across the cloud. These variations are crucial for understanding star formation dynamics. Bok Globule B68 plays a pivotal role in galactic chemistry by recycling heavy elements through star formation processes. As stars form within this cosmic nursery, they enrich their surroundings with metals and other chemical elements. This cycle ensures that future generations of stars have access to the materials necessary for planetary formation, contributing to the chemical diversity observed throughout galaxies. Visible light from nearby stars is heavily obscured by B68's dense molecular cloud, preventing direct observation of its interior. Instead, scientists rely on polarized light and radio waves to study B68's structure and dynamics. This reliance on indirect methods highlights both the challenges and opportunities in understanding such remote regions of our galaxy, offering a window into star formation processes that are crucial for cosmic evolution. B68's interior is a vast laboratory where magnetic fields weave an intricate dance with cosmic rays and dust particles. These charged particles, accelerated by distant supernovae or galactic winds, trace paths along magnetic field lines that crisscross B68's dense core. This interaction not only guides the particles, but also helps to align the molecules within the cloud, influencing how they eventually coalesce into stars. The temperature within B68 can drop as low as -263 degrees Celsius, close to absolute zero. At this extreme cold, molecular motion slows dramatically, and chemical reactions proceed at a glacial pace. Yet paradoxically, despite these frigid conditions, the cloud remains dynamic. Gravitational settling continues to pull particles together, gradually increasing density and setting the stage for future star formation. Within B68's dense interior, the magnetic fields create a network of pathways that are invisible yet crucial. These pathways channel cosmic rays through the cloud, facilitating interactions between charged particles and neutral molecules. This process is akin to how blood vessels transport nutrients in our bodies, but on an astronomical scale. The energy carried by these cosmic rays contributes to the heating and ionization of gas within B68, subtly influencing its evolution. The magnetic fields within B68 are not static. They evolve over time as the cloud contracts under gravity. This dynamic interplay between magnetic forces and gravitational collapse shapes the intricate structure we observe today. The slow dance of particles in this cold, dense environment is a testament to the delicate balance that governs star formation across the universe. In Bok Globule B68, a vast cloud of gas and dust spanning approximately 1 light-year across, magnetic fields weave through its dense interior like invisible ribbons guiding cosmic rays. These fields are not uniform but twist and turn as they interact with the cloud's structure, influencing the paths of charged particles. At temperatures close to absolute zero, around -263 degrees Celsius, the gas within B68 is incredibly sparse compared to Earth's atmosphere at sea level, which contains about 1019 molecules per cubic centimeter. Yet, despite this sparseness, B68's core density reaches an impressive 10,000 molecules per cubic centimeter, a crowded environment in cosmic terms. This contrast highlights the unique conditions within B68. where particles are both isolated and tightly packed. The magnetic fields threading through B68 not only guide cosmic rays, but also play a crucial role in shaping the cloud's internal dynamics. As gravity pulls matter inward, it amplifies local field strengths, creating intricate patterns that influence particle trajectories. This process is akin to how currents shape sediment distribution in rivers, where subtle changes can lead to significant shifts in material flow. Within B68, cosmic rays encounter a complex environment of varying densities and magnetic field strengths. These particles, traveling near the speed of light, interact with gas and dust molecules, occasionally causing collisions that release small amounts of energy. This interaction contributes to a delicate heating effect, adding warmth to an otherwise frigid region of space. The gravitational settling process within B68 has been underway for approximately 500,000 years, but it is far from complete. Over the next 2 million years, the cloud will continue to collapse under its own gravity until it reaches a stable equilibrium. This gradual compression will eventually lead to the formation of several stars, each with unique chemical compositions influenced by the magnetic fields that guided cosmic rays through the cloud. As we observe B68, it's worth considering how these invisible forces have shaped not just this particular globule, but also the broader universe. The iron in your blood was forged in ancient supernovae, and similar processes are at work within B68, contributing to the ongoing cycle of star formation and elemental distribution across galaxies. This cosmic dance of particles and fields continues to unfold over timescales that dwarf human lifespans, yet it is intricately connected to our very existence. The magnetic fields within B68 are not static, but dynamic, constantly reshaping in response to the movement of charged particles and the gradual collapse of the cloud. These fields can be thought of as invisible ribbons guiding cosmic rays through a labyrinthine structure of gas and dust. Each twist and turn of these ribbons is a record of past interactions, marking where collisions occurred or where matter was drawn together by gravity. This intricate ballet of magnetic forces and particles is a testament to the complexity of interstellar space. The paths taken by cosmic rays are influenced not only by the strength of these fields, but also by their orientation. Some rays may be deflected sharply, while others might continue straight through less dense regions. This variability in trajectories creates a patchwork of particle density within B68, contributing to its uneven structure. Over time, this interplay between magnetic forces and cosmic radiation plays a subtle yet significant role in the cloud's evolution. Invisible though they may be, these magnetic fields are detectable through their effects on light polarization. As polarized light passes through regions of varying field strengths within B68, it undergoes changes that can be measured by Earth-based telescopes. This phenomenon allows astronomers to map out the magnetic structure of the cloud, revealing details about its internal dynamics and future star formation potential. While the collapse of B68 is a slow process on human timescales, it is part of an ongoing cosmic cycle. The same forces that shaped B68 are at work in countless other regions of space, each contributing to the intricate tapestry of star birth and death across the universe. This interconnectedness underscores the unity of all celestial phenomena, from the smallest particles to entire galaxies. The magnetic fields within B68 also serve as a reminder of the invisible forces that govern our universe. Just as these fields guide cosmic rays through the cloud, they influence the behavior of charged particles throughout space. Understanding these interactions is key to unraveling the mysteries of star formation. In Bok Globule B68, gas molecules collide at near-light speeds, a phenomenon that might seem impossible given the vast emptiness of space. Each collision occurs with such precision and speed that it would take less than a second for particles to traverse the entire cloud if they could move unimpeded. Yet in this dense environment, these collisions are frequent enough to influence the cloud's structure. The temperature within B68 can drop as low as -263 degrees Celsius, close to absolute zero. Despite this extreme cold, the kinetic energy of the colliding particles remains significant. This paradox underscores the resilience of molecular motion even in near-perfect vacuums. These collisions are not random, but follow a predictable pattern governed by gravity and quantum mechanics. Each collision within B68 triggers subtle changes in the cloud's magnetic fields. As charged particles interact, they distort these invisible lines, guiding cosmic rays through intricate pathways. This interplay between particle motion and electromagnetic forces is crucial for understanding how materials coalesce into stars. It's a dance of invisibles, magnetic fields threading through space, influencing the paths of charged particles. The collisions within B68 are not isolated events, but part of a larger process that began about 500,000 years ago when the cloud started its gravitational collapse. Over time, these interactions will lead to denser regions forming at the core, eventually giving rise to new stars. The energy released in each collision contributes to this gradual compression, pushing B68 closer to its ultimate fate as a stellar nursery. In contrast to Earth's atmosphere, which is dense with trillions of molecules per cubic centimeter, B68 contains only about 10,000 molecules per cubic centimeter. Yet for interstellar space, this density is remarkable and sufficient to allow these collisions to occur at significant rates. The particles within B68 are not merely floating in isolation, but are engaged in a complex dance of gravitational attraction and repulsion. As the cloud continues its collapse over millions of years, the rate of molecular collisions will increase, further compressing the material at its core. This process is slow by human standards, but rapid on cosmic timescales. The eventual formation of stars within B68 marks not just the end of this collapse, but also a new beginning for the elements that will one day be part of other celestial bodies. Each collision in B68 releases tiny amounts of energy, which can sometimes trigger small-scale changes in temperature or density within localized regions of the cloud. These fluctuations are minuscule by earthly standards, but significant on an interstellar scale. They contribute to a delicate balance where gravitational forces pull particles together, while quantum effects keep them from collapsing too quickly. This equilibrium allows B68 to maintain its structure for millions of years, a testament to the fine-tuned nature of cosmic processes. Within this cold and sparse environment, the collisions between gas molecules in B68 are occurring at speeds approaching light. Yet despite their high velocities, these particles do not generate noticeable heat due to the extremely low density of the cloud. This phenomenon highlights an intriguing contrast. While the speed of collisions is incredibly fast, the lack of substantial energy transfer means that no significant temperature increase occurs. The particles simply pass through each other with minimal interaction. The magnetic fields threading through B68 play a crucial role in channeling these high-speed collisions. They guide charged particles along specific pathways, creating intricate patterns within the cloud's structure. This interplay between particle motion and electromagnetic forces is essential for understanding how materials coalesce into stars. It's a dance of invisibles, magnetic fields threading through space, influencing the paths of charged particles. In B68, every collision represents a step in the long journey towards star formation. The energy released during these interactions contributes to the gradual compression of material at the cloud's core. Over millions of years, this process will lead to the creation of new stars, each one forged from the remnants of previous cosmic events. This cycle underscores the interconnectedness of all celestial bodies, where the death of old stars provides the raw materials for the birth of new ones. The particles within B68 are not merely floating in isolation, but are engaged in a complex dance of gravitational attraction and repulsion. As they collide at near-light speeds, they create R. In Bok Globule B68, a vast cloud of gas and dust spanning approximately 1 light-year across, gravitational forces exert a gentle but persistent pull on nearby stars. This interaction subtly influences the motion of particles within the cloud, guiding their paths in intricate patterns. The density within B68 is about 10 molecules per cubic centimeter, which might seem sparse compared to Earth's atmosphere, yet it is dense enough for gravity to play a significant role. The gravitational influence from neighboring stars causes ripples and disturbances within B68, much like the way wind stirs leaves on a quiet day. These subtle motions can alter the distribution of matter within the cloud, potentially affecting where new stars might form in the future. Interestingly, while these interactions are gentle, they have profound implications for star formation processes across galaxies. Bok Globule B68 is not isolated. It exists within a complex web of gravitational relationships with nearby cosmic structures. The cloud's position near other molecular clouds and young stellar clusters means that its evolution is intertwined with the dynamics of these neighbors. This interconnectedness highlights how even in the vast emptiness of space, objects are part of larger systems. The temperature within B68 can drop as low as -263 degrees Celsius, close to absolute zero. Despite this extreme cold, Electromagnetic radiation travels freely through the vacuum of space, allowing astronomers on Earth to study the cloud's internal structure using polarized light and other techniques. This ability to observe such distant and cold regions underscores the precision of modern astronomical instruments. Over millions of years, B68 will continue its gravitational collapse, a process that began roughly 500,000 years ago. As it settles into a more stable configuration, the cloud's edges may become less defined, blending with surrounding interstellar material. This gradual transformation is part of an ongoing cycle of star formation and evolution in our galaxy. The gravitational pull from nearby stars subtly warps spacetime around B68, creating minute but measurable effects known as gravitational lensing. These distortions can bend the paths of light passing through the cloud, offering astronomers indirect insights into its internal structure. This phenomenon demonstrates how even the faintest interactions in space can reveal important information about cosmic processes. The gravitational influence of nearby stars on B68 is not just a passive force, but an active participant in shaping its future. As these distant celestial bodies exert their pull, they can trigger localized regions within the cloud to collapse more rapidly than others. This uneven distribution of mass can lead to the formation of protostars in specific areas, rather than uniformly across the entire cloud. The precise timing and location of such events are influenced by the complex interplay between B68's internal dynamics and external gravitational forces. Each star that forms from B68 will eventually contribute its own gravitational influence back into the surrounding space, further altering the local environment. This feedback loop underscores how cosmic structures evolve over time through continuous interactions. The birth of a single star might seem like a small event in the grand scheme of the universe, but it can have far-reaching consequences for nearby clouds and clusters. Within B68, the gravitational settling process is not uniform across its entirety. Certain regions experience more intense compression due to their proximity to neighboring stars or other dense pockets within the cloud. These areas act as focal points where matter congregates, potentially leading to the formation of multiple stellar systems rather than a single massive star. This variability in collapse patterns highlights the intricate balance between local and global forces at play. The temperature gradient across B68 further complicates its dynamics. While the core remains extremely cold, approaching absolute zero, the edges of the cloud are slightly warmer due to interactions with nearby stars or cosmic radiation. These differences in temperature can affect how gas molecules behave within the cloud, influencing both their movement and interaction rates. The subtle variations in thermal energy contribute to the overall complexity of B68's evolution. The gravitational influence from neighboring stars extends far beyond simply affecting B68's internal structure. It also shapes the broader interstellar medium around it, potentially triggering star formation in adjacent clouds or even influencing the trajectories of distant cosmic rays. This interconnected web of forces demonstrates how At this interface, the dense molecular cloud B68 meets its neighbor, creating a zone where gas and dust particles are exchanged in a slow, deliberate dance. This boundary is not merely a line, but an active region where gravitational forces from both clouds interact, subtly influencing each other's structure. The temperature at this meeting point can fluctuate widely, sometimes reaching as low as -263 degrees Celsius, close to absolute zero. In contrast, just a few light years away, the neighboring cloud might be significantly warmer, showcasing how local conditions can vary dramatically over short cosmic distances. This dynamic interface is crucial for understanding how star formation processes are influenced by nearby clouds. The exchange of particles at this boundary is not random, but follows specific paths dictated by magnetic fields threading through both clouds. These invisible ribbons guide charged particles along intricate pathways, sometimes leading to localized heating events where kinetic energy is released. Such micro-events, though brief and intense on an interstellar scale, are akin to small-scale impacts in Earth's atmosphere, where meteoroids burn up and create flashes of light. In B68, these bursts would be invisible due to the heavy obscuration by dust, yet they play a vital role in the cloud's evolution. Magnetic reconnection at this interface releases energy, sometimes manifesting as jets or shock waves that propagate outwards. These phenomena are similar to solar flares on Earth's sun, but occur on an interstellar scale. The process involves the snapping and realignment of magnetic field lines from different parts of the clouds, releasing stored energy in a sudden burst. This energy release can accelerate particles to near-light speeds, creating a cascade effect that influences the surrounding environment. Despite their intensity, these events are so distant that they do not significantly impact Earth's cosmic neighborhood. The boundary between B68 and its neighboring cloud is also marked by varying densities of gas and dust. While B68 contains about 10 molecules per cubic centimeter at its core, the density near the interface can drop to as low as 10 molecules per cubic centimeter. This gradient creates a complex environment where particles from both clouds mix in intricate patterns. The mixing is not uniform, but follows specific pathways determined by gravity and magnetic fields, leading to regions of higher or lower concentration within this dynamic interface. These variations are crucial for understanding how star formation processes can be influenced by the immediate surroundings. The gravitational settling process at B68's boundary has been ongoing for approximately 500,000 years, with the cloud slowly collapsing under its own weight. However, as it approaches equilibrium, this collapse slows down, and the interface becomes a site of relative stability. This balance is fragile yet essential for star formation within B68. The neighboring cloud's gravitational influence can perturb this delicate state, causing ripples that propagate through the boundary layer. These ripples are like cosmic waves, subtly altering the paths of particles as they move between the two clouds. Over time, these interactions could lead to localized increases in density, potentially triggering star formation at specific points along the interface. At temperatures close to absolute zero within B68, chemical reactions occur at an incredibly slow pace. The cold environment suppresses molecular activity, making it difficult for atoms and molecules to combine into more complex structures. Yet, despite this near stasis, the boundary between B68 and its neighboring cloud provides a unique opportunity for interactions. Here, particles from both clouds can collide, leading to rare but significant reactions that might otherwise be impossible in such an extreme environment. These collisions are not violent but gentle encounters, where particles exchange energy and momentum without breaking apart. This delicate dance at the boundary could play a crucial role in the eventual formation of stars within B68, as it helps prepare the cloud for the next phase of its evolution. Within Bok Globule B68, a vast cloud of gas and dust spanning approximately 1 light-year across, particles are engaged in an intricate gravitational dance. These collisions occur at near-light speeds, a phenomenon that might seem impossible given the vast emptiness of space. Each collision happens with such precision and speed that it would take less than a second for particles to traverse the entire cloud if they could move unimpeded. This process highlights how gravity shapes not just individual particles, but entire regions of space, sculpting clouds like B68 into potential stellar nurseries. Bok Globule B68's core is an environment where temperatures plummet close to absolute zero, yet it glows with a faint light. This radiation emerges from the densest parts of the cloud, where particles are packed tightly together at about 10⁴ molecules per cubic centimeter. Despite this density, which is high by interstellar standards, B68 remains an extremely sparse environment compared to Earth's atmosphere. The glow in the core contrasts with the near invisibility of its edges, a testament to how light behaves differently in dense and diffuse regions. This contrast reveals the complex interplay between temperature and opacity within the cloud. The collapse of B68 is not isolated, but part of a broader cosmic narrative that includes interactions with nearby clouds. These neighboring structures can influence the gravitational settling process by adding or removing mass, altering the dynamics of star formation. For instance, a nearby supernova shockwave could stir up the quiet depths of B68, accelerating its collapse and potentially triggering new star births. This interaction underscores how individual cosmic events are interconnected within galaxies, shaping not just one cloud, but entire regions. Bok Globule B68 contains roughly 2 solar masses of gas and dust, with the potential to form several stars over time. The iron in these future stars was forged in a distant supernova explosion that occurred before our Sun even existed. This ancient material has traveled through space for billions of years, only now coming together under gravity's pull. It is this recycling of elements across cosmic timescales that ultimately contributes to the conditions necessary for life on planets like Earth. The iron in your blood was once part of a star that died long before our Sun was born. In B68, magnetic fields weave through its dense interior like invisible ribbons guiding cosmic rays. These fields are not uniform, but twist and turn as they interact with the cloud's structure, influencing the paths of charged particles. This intricate dance of magnetic forces shapes the environment within B68, creating a complex web that affects how particles move and collide. The interplay between gravity and magnetism in this region demonstrates how multiple physical processes work together to sculpt cosmic structures. As we reflect on the journey through Bok Globule B68, it becomes clear that despite its vast emptiness, this cloud is teeming with activity. At -263 degrees Celsius, close to absolute zero, each particle within B68 is engaged in a delicate dance dictated by gravitational forces. This region of space, once thought merely static and cold, reveals itself as a dynamic environment where stars are born from the ashes of ancient supernovae. In this quiet expanse, life's conditions on Earth may have been subtly influenced by processes that began billions of years ago, far beyond our solar system's reach. In the vast silence of deep space, Bok Globule B68 continues its ancient dance, each particle a silent witness to cosmic time. As this serene journey draws to a close, let us pause in this quiet expanse for just a moment longer. Thank you for joining us on this tranquil voyage through the stars. Don't forget to subscribe and like if you enjoyed the ride. Good night, Chinese letter, Chinese letter, Japanese letter, Chinese letter, Chinese letter, Japanese letter, Chinese letter, Japanese letter, Japanese letter, Japanese letter.